Guten Morgen oder guten Nachmittag, meine Damen und Herren. Welcome in on Atlanta. This is Brad Van Meter with Herrenknecht Corporation, and we're broadcasting live this morning from the Metropolitan Atlanta East Line Extension Project. We are located approximately 5 miles from the center of the city. The East Line Extension, when it's completed, will connect parts of Decatur, Georgia, in DeKalb County. This extension will soon provide a vital link to MARTA's overall extension project, which is due to be completed by the end of the decade. The East Line Extension will serve to commute people to the scheduled 1996 Summer Olympic Games that are to be held in nearby Stone Mountain Park, east of this site. It's presently 9:45 Eastern Standard Time, and we're at the end of the rush hour traffic. The rush hour and the heavy traffic on this thoroughfare were one of the key reasons for the construction of this tunnel. Twin single-track transit tunnels were designed to cross underneath the interstate. A multiple pipe arch of interlocked steel casings was designed to provide the necessary primary foundation for the support. Underlying the arches are preformed steel rib sections, which are keyed into the supporting bedrock with constructed mini piles. The finished tunnels are lined with concrete. Joining me today is Ulrich Lemke, Chief Structural Design Engineer for Parsons Brinckerhoff Tudor Consulting Engineers, who did the primary design for the East Line Extension project. Also is Joe Appleton, who is the project manager for Archer Western Contractors Limited, who's the general contractor for the project. Good morning, gentlemen.
Good morning. Morning.
Good morning. Ulrich, as we view the nearly completed tunnels, how was the pipe arch support design selected by Parsons Brinckerhoff for the project?
Well, our primary concern with the tunnel, Brad, was the potential for ground loss during the construction, and since we have very shallow cover over the tunnel, we selected the multiple pipe arch method as the means to provide advanced support prior to excavation and to reduce settlements.
What were some of the alternate methods that were considered for construction?
We looked at a jacked precast concrete lining, we looked at a ground freezing, and also at the multiple pipe arch. And the ground freezing approach our main concern with that was that we might have some potential settlement or potential heave during the freezing process, and then possible localized settlement during the thawing. Mm-hmm. The jacked precast concrete lining we were thinking was probably more suited to tunneling under railroad embankments, where you could take up the potential settlements with reballasting of the trackway.
Yes.
So we felt the multiple pipe arch really offered the best solution for this particular site.
Joe, from a contractor's perspective, logistically, what were some of the demanding features of this project to coordinate the efforts between the specialty subcontractors?
Well, the primary problem was the coordination required between the many different construction activities involved in the tunnel. We had to coordinate several crews and different pieces of equipment, crews both employed by Archer Western as well as our specialty subcontractor, SEC. When the job went from microtunneling to jet grouting to mini piles to tunnel excavation, contact grouting, and then for excavation. So that was quite a challenge.
Good. Has the project proceeded as planned, or the tunnels being completed ahead of schedule?
Yeah, the tunnels are currently on schedule in spite of a late start in the tunneling activities. The microtunneling activities actually proceeded quicker than what we had anticipated prior to construction.
Let's take a look at this very unique process in closer detail.
Trenchless technology, a name synonymous with the science of constructing unmanned subterranean utility installations. Once considered to be theory of a few futuristic innovators, trenchless technology has expanded to touch the daily lives of people everywhere. by minimizing both social and economic disruption created by conventional construction methods. In a world where out of sight is out of mind, trenchless construction has proven to be a tremendous benefit to today's urban commuter. A unique method of tunnel construction was recently selected to extend the East Line commuter railway system for the Metropolitan Atlanta Rapid Transit Authority, MARTA, in Atlanta, Georgia. Atlanta has developed into the largest urban metropolitan district within the southeast United States, the 9th largest city in the country. Atlanta rules as the financial, economic, and transportation center of the South, with a population of over 2.8 million people. To provide for Metro Atlanta's continued expansion, the East Line extension was designed to connect parts of Decatur, Georgia, in DeKalb County, approximately 5 miles from Atlanta's famed natural attraction, Stone Mountain, a monolithic mesa of solid Georgia granite. The East Line crosses under Interstate I-285, one of the busiest suburban outer loop thoroughfares in the nation. Originally constructed during the 1970s, I-285 serves to relieve traffic congestion from Interstates I-75, I-85, and I-20, which all intersect in Atlanta. Over 200,000 commercial and commuter vehicles pass the tunnel site within a 24-hour period. Parallel single-track transit tunnels were designed to cross the 8 lanes of highway leading to the new Indian Creek station. Logistically, MARTA determined that the better choice would be to cross the thoroughfare with a tunnel as opposed to a bridge, which would have required considerable changes in track elevation as well as extended maintenance. The major design challenge posed to the project was how to protect the shallow depth of less than 5 feet between the crown of the tunnel and the roadway surface. As a vital design prerequisite, a method of tunnel construction had to be selected which would maintain the integrity of the infrastructure throughout all phases of the project. A multiple pipe arch of interlocked steel casings was selected as part of the primary foundation for the tunnel. During the investigation of the soils present at the site, it was determined that the majority of the tunnel would be in undisturbed residual strata. The critical sections near the tunnel crown were determined to be imported soils placed during the construction of the highway. Though boulder conditions were not anticipated as major obstructions, the possibility of their existence could not be discounted. Preformed steel rib sections set with shims under the support of the arch are keyed into the supporting bedrock with constructed mini piles. A concrete finish lining completes the parallel horseshoe-shaped tunnels. The dimensions of each are 21 feet in width, 23 feet in height, and 178 feet in length. Contact grouting around the support pipes and horizontal jet grouting of the tunnel heading were determined to be crucial to provide further protection for the highway. MARTA selected the design engineering team of Parsons, Brinkerhoff, Tudor, Consulting Engineers of Atlanta for the project, and Golder Associates Incorporated as the geotechnical consultants. Archer Western Corporation of Georgia was awarded the work as the general contractor in April 1990. Archer Western, in turn, selected Salgado Eastern Corporation of Columbia, Maryland as the pre-qualified subcontractor for the macro-tunneling portion of the overall project. SEC was the first contractor to use macro-tunneling technology in the United States in 1984 with the installation of a crossing under Interstate I-95 near Miami, Florida. Macro-tunneling is most often utilized for constructing underground utilities of diameters that prohibit manned access and entry. The process utilizes the principles of pipe jacking with the integration of remote control for one-pass utility construction. Laser guidance and computer interface enable the placement of pipe structures with assured accuracies. The pipe arch supports represent an excellent crossover application for this equipment, since very precise placement of the pipes was required. A Herrenknecht AVM 600 micro-tunneling system was selected by SEC Corporation to install the 42-each, 30-inch diameter steel pipes, which comprise the twin arches. The Herrenknecht system was chosen over all others due to its previously proven disc cutter head feature exclusively designed for boulder conditions. The Herrenknecht AVN system utilizes a slurry spoil removal process for soil transportation to the surface. Each pipe section installed contains intake and exhaust slurry lines within the closed circuit. raw water introduced into the chamber directly behind the cutting head mixes the excavated material into a liquid medium for pumping to the surface. Decantation of spoil settlement takes place on the surface, whereby solids filtrate out of the slurry with recaptured water being recirculated back to the machine. The AVN machine excavates with a birotational cutting head with the maximum torque capacity to handle changes in soil conditions. A horizontal coffee mill crusher is integrated into the AVN design to reduce any material excavated by the cutting head to a maximum size of 3/4 inch aggregate. The AVN slurry design enables the machine to be used in submerged conditions by counterbalance of the water introduced into the slurry chamber for spoil transportation. The liquid in the slurry circuit is matched in pressure to the static groundwater pressure present at the face. Volume of the pumped liquid into the machine is balanced with the slurry removed. This feature was not a factor for the Atlanta project due to dewatered conditions present. As a result, the water which was injected into the crusher chamber was maintained towards the rear of the vortex. Dry material is compacted towards the rear of the chamber before being mixed. This provided additional security that slurry was kept to a minimum at the heading and was not introduced forward of the cutting head. The cutting head of the machine provided a minimal overcut of 3/8 of an inch on the diameter over the steel pipe. The annular space was filled with an injected bentonite, fly ash, and grout mixture introduced through lubrication ports in the machine. Bentonite pumping equipment was included in the Herrenknecht system and could be operated when required by the machine operator. A specially designed jacking frame, which supplies over 340 metric tons of thrust, was furnished by Herrenknecht to install the 20-foot lengths of steel pipe. All of the micro-tunneling drives originated from a common launch shaft, which adjoined the parallel tunnel headings. The crown tunnels were installed first, with excavation alternating from tunnel to tunnel. The shaft was excavated in graduating levels as the micro-tunneling proceeded down toward the invert. Jacking subframes were furnished with the equipment to enable quick setup of the next pipe drive on the adjacent tunnel, as the micro-tunneling machine was demobilized from a previous drive. Specially designed pipe sections were prepared for the MARTA project, with a steel T-bar attached to the outside diameter of each pipe section. As each pipe was positioned to be placed by micro-tunneling, the T-bar was inserted into a receiver slot contained within the inside diameter of the adjacent pipe. As the pipes were installed, the interlock formed by the frame and receiver bridged the gap between the pipes to eliminate subsidence and settlement from the surface. Connections for joining the steel pipes were made with a slip joint formed by an internal line-up band that was welded to the inside diameter of one end of the pipe sections. The band formed a tongue joint connection which was tack welded during the jacking process. Final welding took place from the inside of the pipe sections after placement, just prior to filling the pipes with grout. Since all of the pipe sections were backfilled with concrete, many of the pipe joints were bridged with steel reinforcement cages that were affixed to the inside of the pipe. This eliminated welding of the pipe joints entirely and resulted in a significant time savings. Quick-setting polyurethane foam was injected into the box beam receiver slots of the pipe sections to prevent slurry, which may have escaped around the periphery of the pipe, from filling the space. Foam was also applied to the tunnel face after removal of the steel sheeting to reduce sealing requirements for launching the machine. All power supply for the micro-tunneling machine is housed in the service container, which was positioned between the tunnel headings. Hydraulic lines for all machine functions are added with each installed pipe section, along with electric power supply for the machine's guidance system. Steering control of the gradient and alignment of the tunnels are maintained by the articulated head of the AVN. Double-acting steering cylinders reposition the head to correct deviations during the drives. Steering control is monitored and directed by the Herrenknecht Active Laser Target Guidance System. The system receives the generated laser beam from the launch shaft and translates all tunnel data to the operator every 3 seconds during the tunnel drive. Control for all functions of the tunnel system take place from the command console located in the service container. The exclusive Herrenknecht computer laser interface feature serves to record all functions of the machine and coordinates of the tunnels throughout the tunnel drives. The computer's mapping feature provides permanent documentation of all machine functions and causative guidance, which is a result of the encountered ground conditions. Microtunneling progressed from startup in late January 1991, and all of the 42 crossings, totaling 7,560 feet, were completed by mid-June. The best achieved production was the complete installation of one 180-foot drive in two 10-hour shifts. The best time recorded for adding an additional pipe section was under 20 minutes. The concept of a multiple pipe arch pre-support placed by microtunneling, integrated with horizontal jet grouting and support through final excavation, well satisfied the stringent requirements of the state and federal departments of transportation. The combination successfully met the challenge of a logistically demanding project. The MARTA project proved that the method of microtunnel pipe arch installation enables large diameter structures to be constructed in difficult or sensitive soil conditions at very shallow elevations. Trenchless technology advancements now cross over to provide more new and innovative construction designs for the future. Regardless of the application, from minuscule 10-inch diameter microtunneling requirements to mid-range excavator and road header systems to large diameter mix-shield systems exceeding 38 feet, Herrenknecht provides worldwide service and support to handle all tunneling applications.
Ulrich, how was the multiple pipe arch system cost effective as compared to some of the other systems that you considered?
Well, as a matter of fact, it was probably the more expensive method of the ones we looked at. The cost was about $24,000 per foot of tunnel, but we were really more concerned with the control of settlement than evaluation of first cost. And one of the things that we did give quite a bit of consideration to was the cost of potentially having to replace the Portland cement concrete pavement above the tunnel if we did have settlement.
Yes. And what is your opinion of how trenchless technology was integrated into this overall project?
Well, without question, I think the trenchless technology or the microtunneling was really the key ingredient to making the system work, because we needed to have an accurate means of installing the 30-inch diameter pipes. Without trenchless technology, I think we probably would have had to select a different means of construction.
Joe, this project has gained a lot of attention, as you well know, within this country. There are several project owners and design engineers that have similar projects of this scope. How does Archer Western feel that they would participate with the experience that they've gained from this project?
Well, we certainly hope we could, Brad. This has been a very challenging project and we've learned a lot on it, but we're pleased with the way it's turned out, and that's saying a lot because before we started the project we saw it as a project with a high degree of risk.
Did the project meet the demands of MARTA, the owner?
Yes, I think it did. I think MARTA is overall very happy with the way the job has turned out. There were a bunch of specialty contractors involved in the work, the microtunneling, the jet grouting, and the pipe piling, and there was some advanced work required to pre-qualify contractors for that work. But I think that's paid off, and the learning curve seems to have been fairly short on each of the activities, and I think the job is being completed on schedule and within budget.
Good. What about the federal and state regulatory agencies that oversaw this project?
Well, the Georgia Department of Transportation and the Federal Highway Administration were the two reviewing agencies, and they really had very little concern about the job. They had very little comment.
Would you recommend this system again for a similar project?
Oh, I think so. I think any job where the overriding concern is control of settlement, I think this system is very applicable. We did, as Joe mentioned, we did learn a few things along the way that we could probably do a little differently and improve the system, but I think it's very applicable.
Gentlemen, I'd like to thank you for both taking the time to comment on this very challenging and logistically demanding project. And Hamburg, we'd like to thank you for the opportunity to discuss trenchless technology applications whereby microtunneling was used to construct macro diameter tunnels. We invite you to the 8th International No Dig to be held next April in Washington, D.C., and we bid you auf Wiedersehen and goodbye from Atlanta.